Welcome to Integrated Math 3. On this episode, Stevenson will demonstrate Let's look at transformation B now. To illustrate transformation B, this time I chose to do a cosine graph. Please understand though that when I show you all these transformations, whether I use cosine or sine, the effects are still the same. So don't stress. I just decided to go back and forth between the functions to give you some variety. So let's look at the first one here. In this case, I made the B value 2. So I have a horizontal dilation where a B is 2. The question is it going to compress or stretch? Well, because B is bigger than 1, what's going to happen is it's going to take this cosine wave and it's going to compress it towards the y-axis. So I want to make a table of values here to show you that. So just like last time with the sine wave, when we did transformation A, we picked certain values. The difference though in this case is that these x-intercepts will actually move because we're moving horizontally now. With transformation A, only those outputs, those maxes and mins, moved above or below where they were originally. So let's start with pi over 2. If I have pi over 2, so I'm looking at this point here, I'm going to plug it into my cosine function. But my cosine function says take 2 times whatever you plug into it. So I'm going to do 2 times pi over 2. Well, that really means I'm doing the cosine of pi. Well, what's the cosine of pi? Look at your unit circle. It's -1. So that means at pi over 2, I actually have a point here at -1. Well, that's weird. Let's keep going. Let's check out pi. Cosine of 2 times pi is really cosine of 2 pi. Well, that's +1. So at pi, I have +1. So what I'm going to do is I'm just going to do enough points so I can get a pattern, and then I'm going to repeat the pattern on the other side. Let's try 3 pi over 2. So that's going to be cosine of 2 times 3 pi over 2, because remember that's what's happening to my cosine function. Well, when I have 2 times that, it's going to simplify with the 2 on the bottom, so that's really cosine of 3 pi. Whoa! Okay, so what that means is you're going to go around your unit circle 1 pi, 2 pi's, 3 pi. So you're actually over here on the unit circle. So that's going to be -1. Now let's try 2 pi. So 4 pi means you've gone completely around the circle 2 times. So it's back up to 1. Let's try 0 and see what happens there. So I think we have enough here to complete the pattern. So the next point is probably going to be 5 pi over 2. Let's just calculate it just to be safe. I'm suspecting it's going to be right about here. Okay, 5 pi. So you're going to go around the circle 5 pi. So remember, 1 pi is half a circle. So you're going to go 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. So that's -1. Okay. So then 3 pi, so let's look for a pattern here. So it looks like at the whole pi, so 0, 1, 2, 3, the point is up here at +1. But at the half pi's, it looks like it's down at -1. So let's continue that pattern over here. So -1, -1, -1, -1, +1, +1, +1. Now let's do our sketch. So if you look at this, I know it's kind of weird, but if you notice, the orange graph is repeating itself faster. It's oscillating faster. It was compressed. Because B is more than 1, it horizontally compressed the graph. It actually was compressed. It took half the time to get where it needs to be. Now you might be thinking, but Stevenson, the B value was 2. Why'd you do a half? There's a reciprocal relationship here. Here's how I know. You ready? What's the period in the original graph to do one cycle? It's 0 to 2 pi, isn't it? Now ask yourself, what's the period of the orange graph? 0 to pi. It took half the time. So it compresses the graph by 1/2. So it's going to take half the time for this orange graph to achieve one cycle compared to its parent function.